Okay, so we looked briefly at the ideal diode model, and we know what the VI curve looks like for the actual diode, and that's going to be on the left here. So this would be our forward bias region, where we have at the knee voltage, we have current flowing through, which is that kind of vertical turn to the graph. And then in the reverse bias region, we have this very, very small nanoamps region reverse bias current that can flow. So for the ideal diode model, we're modeling the diode as either an open switch or a closed switch. When we have a closed switch, we have 0 volts across it. So that's our forward bias model for the diode. This is our closed switch. We can have basically any current flowing through it, but we have 0 volts across it. So that's why we have this at 0 volts, but we can have any current value. And then for the reverse bias region, we have 0 current, right? Because then it's acting like an open switch, like that. So there's no complete path for current to flow, so it has to be 0 amps of current, but we can still have different voltage values across it. So that's why we have our horizontal line there. So this does somewhat match up with our actual VI curve for the diode, because that looks kind of like this. We've got that kind of a gentle curve. But the difference is, that's supposed to be a straight line. The difference is that it makes that vertical turn after this vertical axis, so after 0 volts. But for our ideal diode model, our model for the reverse bias region, that's pretty much fine. It follows along this axis, and that's okay because we have such a tiny reverse current that it doesn't really matter. But when it makes that vertical turn, it makes it at 0 volts instead of at the knee voltage. So it somewhat matches the curve, just ignoring that slower bend, but it makes that turn a little bit too fast because we're allowing current to pass through at 0 volts instead of whatever the knee voltage actually is for that diode. Okay, so that's why we have a different model that we're going to get to here, and that is the knee voltage diode model. And that's very similar to the ideal diode model. We're just going to shift that curve a little bit over so that it more closely follows the actual characteristics of a real diode. Okay, so our formal statement for this is right here. And this is going to be the model that's considered good enough in most cases, so it's going to be what we use most often, and we actually have used it a couple times without actually naming it so far. So a sufficiently forward biased diode, so it's hooked up in forward bias, and it has enough of a voltage applied to have current flowing through it. A sufficiently forward biased diode acts like a voltage source in that it drops a reasonably constant voltage independent of its forward current. So whatever current is flowing through it, it's going to drop a consistent voltage value, which is what we were observing in the lab, where the diode voltage maintains about 0.7 volts, regardless of what voltage we apply and what current is flowing through it. So that voltage is approximately equal to its knee voltage, which would be for our silicon diode about 0.7 volts. And in this knee voltage model, a reverse bias diode acts like an open switch. So that remains the same as we saw for the ideal diode model, because that part of the model was working just fine. Okay, so the only difference here is that when we have a sufficiently forward biased diode, we model that not as a closed switch, but as a new voltage source. So instead, we're just going to have this VR. So this is our voltage across the resistor, and that value is going to be equal to our voltage source minus whatever our diode voltage is, and that's going to be equal to the knee voltage, because once we have a sufficient voltage applied, that diode voltage is going to stay consistent at about the knee voltage value for whatever that diode material is. Okay, so we have ID equal to this formula, and we've kind of derived this a couple times so far, so it should look a little bit familiar. And then for reverse bias, it's exactly the same as before. For the ideal diode model, we just have this reverse bias diode. So we say, all right, for this model, I can model that as an open switch, which means there's going to be zero current because we have no complete path for current flow. And since it's an open, that voltage is going to be equal to whatever the source voltage is. In this case, it's 15 volts. Okay. So that's our formula. If we wanted to do an example, let's say we had a silicon diode. So a silicon diode means that we have a knee voltage that is about 0.7 volts, and that's what we see right here. And we want to find the diode's forward current ID. So it's forward biased. We know that this is going to be our formula that we want to use. We're given that we're looking at the same circuit that was shown earlier, and in that circuit we had Vs equal to 15 volts. We had some resistor value, which was 2 kiloohms, and a forward biased diode. So we know this is given, Vs is given, value of the resistor is given, that the diode is hooked up in forward bias is given. It's a silicon diode, so we know that knee voltage is 0.7 volts. And that means we have everything we need to find the diode current. And that will be Vs minus Vk, all that divided by R. So we have 15 volts minus 0.7 volts divided by the value of the resistor, which is 2K, and that gives you 7.15 milliamps. So if we were to repeat this, but with a germanium diode, so it's a different semiconductor material, what would change is this knee voltage right here. So different semiconductor material would mean that now we have a knee voltage of 0.3 volts. So germanium means that our knee voltage is 0.3 volts. So we would, instead of 0.7 right here, we would put in 0.3, and that would give us a different current value. And I believe that that is done. Oops, the wrong screen there. So that should be done in this example right here. Yeah, so we have 0.3 volts instead, and that's going to give us a slightly higher current value. So instead of this 7.15 milliamps that we had for the silicon diode, we have 7.35 milliamps. So not a huge difference, but there is a difference. Okay, so using that knee voltage model, that gives us a slightly different VI curve. And this more closely matches up with the real life curve. So what we had for, real life, we have this curve that has a bit of a bend here where the knee voltage is. For the ideal, so this is real, ideal, and I'll put the knee voltage model down there. So for the ideal model, we just had an open or closed switch. So our VI curve looked like this. So it's fine for the reverse bias region in this area here, but it doesn't really match up for the forward bias region for our real model. But then we just take this and shift it over a bit with the knee voltage model. So We still have our forward bias, or I should say our reverse bias region here. And then we're starting to get into forward bias in this area right here, but we don't have a sufficient voltage applied to actually have current flow. So that's kind of like this area right here. And then when we get to the knee voltage, VK, we have that abrupt vertical turn where we have a voltage source hooked up, and we can have any current flowing through that, but there's going to be a fixed voltage drop, and that is equal to the diode voltage and the knee voltage, VK, for that particular diode material. So this is a simplification, but it's a much more accurate simplification, and it works pretty well for modeling our actual behavior for the diode. Okay, so I'm going to pause that right here for now.